Today I will give you a presentation about deep learning neural networks. The presentation contains following parts. First, we'll start with a small interesting story. Then I will give you the big pictures of what machine learning is. Then we'll cover main topics of machine learning. The first one is unsupervised learning, which includes clustering, dimension reduction. The second one is supervised learning, which includes regression and classification. Then on top of classification, I will give you more specific model, which is neural network. And we'll show you how it can solve a classification problem, handwriting recognition. Then on top of that neural network, I will show you how a deep learning neural network can be built from it and to improve its performance. So let's start. So first, a story. There's a legendary story about how machine learning can help to gain unexpected insight of data. So there was a supermarket of supply chain. They found that there was a high correlation between beer and the diaper. So the sales of beer and diaper. So from this information, what kind of insight can we get? By reasoning, we can understand that usually daddy was sent to buy the diaper. And while they're working in the store, what else do they buy? They probably will buy beer as well. So that's the insight of this, this discovery. So with this insight, what strategy can we take, can the store take? So one strategy is that we can put the beer next to the diaper, so it will remind the customers. The other strategy you can take is that put the beer away from the diaper, so the customers will walk around the shop and they will buy more stuff. The last strategy I will discuss is you can actually do a promotion on diaper, decrease the price of diaper, but you secretly increase the price of the beer. What's going to happen is all the customers will come to your store to buy diaper, and they will also pay extra money for the beer. So in this story, there's little more insight. So the question is, who lost? The customers actually doesn't pay more money because of the promotion. Your store actually sold more beer and the diaper. So the answer is other stores. So by using this strategy, actually customers come to your store. So this is just a story to start. Okay, so now we talk about the big picture of data science. So look at the picture on the right. A data science actually is a crossed knowledge of three main areas. Computer science, we all know what it is. Domain expertise. What domain expertise means? The knowledge of the area you want to study. So, for example, the previous example, we know that buying diaper actually leaded to buy beer. So this is domain knowledge. If you have no idea what diaper is, what beer is, you wouldn't be able to do the reasoning. And the other thing is that look at this picture in the middle. So this is actually a spring clock of a car. If you are trying to sell a car and do data mining on car parts, so you better know what this is, right? So this is domain expertise. So the last part is mathematics. So actually, in mathematics, there's two important areas. We will be talking a lot of machine learning, of course, I just want to give you a mention of statistic research. So continue with this beer and the diaper story. So what we can think is that a question we can ask is, what if the relationship between beer and the diaper is not so obvious? You cannot reason by your expertise knowledge of this area. You don't know which leaded to which. Statistically, we can do research to find which leaded to which. Say we randomly select 100 men and split them into two groups, 50 by 50, and assign the first group to buy beer plus one item they can choose with their own money. And the other group, we assign them to buy diaper plus one item they can choose with their own money. So then you collect the result. What do you expect to see? I think the group which bought diaper then bought beer will be much higher than the group who bought beer plus diaper. Why would you buy a diaper if you don't have the needs, right? If you go to a supermarket and want to buy a beer, you probably won't buy a diaper. So by doing this experiment, you can discover that buying diaper actually leaded to buy beer, not the other way around. Statistically, there are two statements describe this experiment. So random selection can be generalized to a larger population, and the random assignment can infer causation, which caused which. Okay. Less small, big picture here. So now we zoom into machine learning. So a very vague definition of machine learning is it's a type of artificial intelligence that provides computer with ability to learn without being explicitly programmed. So there's no if-else rule type to solve the problem. You don't need to do that. A more formal definition, I actually have simplified this definition because it's very long. So a computer program is said to learn if its performance P at a task T improves with experience E. I'll give you an example. Question. We have a program, it can learn to filter out spam emails. So what is T, P, and E? So in this case, I think T, the task, is to filter out spam emails. P, the performance, is what's the rate of correctly filter out the emails. Good program will filter out 99% spam emails, bad maybe just 50%. That's the performance. So what's experience? Experience is the emails coming to your mailbox. With more emails coming, your program may learn better. With 100 emails, your program may learn do the classification at 50-50, but with 1,000 emails, maybe the correct rate increased to 90%. So these are the TPE. One more interesting question for all the programmers, is Java a machine learning program? In some extent, I think it is. It has a JIT compiler. During warm-up, the execution speed of your program can be improved. So in this case, the task is to run faster. The performance is, the P is to measure how fast the latency of your program, and the experience is a warm-up code you write, which trains the Java compiler. That definition was by Tom Mitchell.
Oh. Including the Java part?
Not the Java part. Java part. I invented the Java part. Okay, so main areas of we now know what is machine learning. Main areas of machine learning. I think the two most important areas of machine learning is unsupervised learning and supervised learning. Unsupervised learning is a machine learn tasks from unlabeled data. No one tells you which is wrong, which is correct. Supervised learning is the other way around. You learn from labeled data. You know what is correct and what is not. Okay, let's jump into maybe a quick words about this diagram. So on top of unsupervised learning, there will be clustering, dimension reduction, and on top of supervised learning, inside supervised learning includes regression, classification. Of course, there are many more models, methods we will not cover. But all the things you see here, we will try to at least mention. Right? So now I'll start with the unsupervised learning example, clustering. Let's start with a problem, an example. So say you are making t-shirts, and to save the cost, you just want to make 3 sizes, small, medium, large. You have many data, people's weight, height. How do you design the size of your t-shirt? Look at the picture on the right. These dots are the people, are the input you collected, height, weight. A reasonable grouping of the data seems to be the 3 blue circles. You want to group these data into, if you want to design 3 sizes, the small size better to cover people with such kind of height and weight. The medium cover this part, the larger cover this part. If you, sorry, you probably don't see this. I'll repeat. So if you, the small may cover this part, medium cover this part, larger cover this part. If you're, so this seems to be a best solution. So the computer program which can solve this problem is called k-means. In this case, you define k equals 3, and the computer program, the algorithm, will find the best solution to group the people into the 3 groups. We'll not go into the detail, but throughout the presentation, we'll have more and more details. The second model I would like to present is the dimension reduction. There's a very popular method in dimension reduction. It's called principal component analysis. So the example I want to introduce is image compression. It's a loosey compression, which means you're allowed to lose information. This happens to a lot of image processing, but latest technology actually doesn't use PCA. So when you open a JPEG picture, it doesn't use PCA. So what kind of problem do you want to solve? So say you want to compress the data on the right. So you have the data, the black dots, the data. So how you describe this data? Easy. X equals 20, Y equals 10. That's 1 dot. The other dot, 40, 20, something like that. So you save all these 20, 40 in a file. Say you want to compress data in half. Remember, you're allowed to lose information. Well, very easy way, what we can do, just forget the Y. We just keep the X, right? So we forget all the Y. We lost a lot of information, but at least we somehow still know the X. So all the data will drop to this line. This is not so good. We lost too much. So a better solution is we can change the basis, the axis first. So what if we change our x and y to this blue line and this red line? So actually the blue line will catch a lot of changes in these black dots. So then if we drop the red axis, we don't lose too much. So all we need is to know how to do the transpose, how to change the base, and then we just save all the axes. Then we can recover. All the dots will be along this blue line, but we don't lose too much. So this is the idea of dimension reduction and how PCA works. I will not cover how we do it because a lot of math is involved. So, but just to quickly give you the information, actually it's very easy to apply this logic algorithm with computer program. You do the covariance matrix of the data, get the eigenvectors, then lastly you apply the matrix operation. We don't need to remember these things. However, one thing to note is that this model compared to the previous model, actually this model is mathematically quite hard to prove, to learn. It covers a lot of areas of mathematics. You need to know linear algebra, you need to know covariance, what covariance matrix is, you need to know eigenvalue, you also need to know Lagrange multiplier, I think he is a French guy. You also need to know what orthogonal matrix is, so a lot of things. But the previous model, this one, the K-means, it requires no math. So if you think you understand this one, implemented it, and then you move into this PCA, you'll find it's very hard to, it takes a lot of time to understand. Okay, so let's conclude all the unsupervised learning. Now we will move to supervised learning. The first model I would like to introduce is linear regression. This is a very popular model. The reason I want, the main important thing I want to tell you first is that this linear regression model actually contains a lot of basic ideas of supervised learning. So if you understand this model, how it works, you will have no problem to understand other models. But of course, the model itself will be different. So let's start. Supervised learning, linear regression. So the problem, I'll give you a simple problem. So let's say we have a lot of data about the price of house and its size. So obviously they have some kind of relationship. On the right, you will see the training set of house price, house size and price. One row is one sample you want to take to train your program. So from this data, you will have a lot of examples. You will have a lot of samples, 1,000, 10,000 samples. Size will be your input, and the price will be your output. So you want to learn you want to predict the price from the size. So how the model works? The model takes the data as an input, and your program will learn from the data you provided, and eventually it will become more and more correct. Right? So let's see what the model is. This is mathematically probably the simplest model. I think everyone can understand it. So the x here is the size, and we have two parameters, theta 0, theta 1. So the output is the price we want to predict. So if you plot this one, everyone, I think most of people understand this is a line. This is a line, a red line or black line. Depends on what theta 0 and theta 1 is. So this is the model you want to learn. Specifically, theta 0 and theta 1 are the final parameters we want to learn. So our goal is that from this training set, from this predefined model, but the parameters can change, to learn, eventually to learn the theta. You don't need to really look at the formulas. So the idea is that, go back to the, so we define a cost function which shows how good your line fits the data. So then, if you can minimize this cost function, you will have a line which fits your data best. So how to minimize this cost? There's a very important concept I want to cover, which is called the gradient descent. Forget about the linear regression, forget about it. So any function, for any function, if you want to find theta 0, theta 1, theta 2, theta 3, which minimize that function, we can use gradient descent to do that. What we do is randomly select theta 0, theta 1. Then we find out the gradient. What it means, mathematically it's partial derivative, but what it means is to which direction the function, the output of the function goes down. Then you go that direction with many steps. Then you apply this technique again and again and again until your function doesn't go smaller. Then you found the theta 0 and the theta 1, which minimizes this function. This gradient descent will be used in all the models that we will discuss later. So, okay, so that's probably it. We will put it all together to explain you how it works. So we have a model to predict the output. This is called hypothesis. We have a model. Every time we take one sample, feed it, and see what's the output. Then the output is not accurate all the time. So it will have a cost, which is the difference between the output and the expected price. So the cost function shows how bad is your hypothesis. So after going all the samples, applying the previous gradient descent I have mentioned, you will be able to improve your parameter theta a little bit. Then if you loop through this scenario, eventually you will find the theta and you will find the best fit. So it's worth to mention there's actually a linear algebra solution. You can directly find x, but we don't discuss about it now. Okay. So now we move to classification problems, supervised learning classification problems. So classification problem, the example is, let's say we have input of tumor size, and we knew already if it's benign or malignant. So to show this input data, we can see here that if the size is small, it's good. If it's big, it's probably not bad. Right? So then we define a threshold. If we go back to this picture, so this one. So then we define threshold of our function. If the output is bigger than 0.5, it's bad. If smaller, it's good. So let's first look at how linear, we already have a model which is linear regression. Let's have a look why linear regression is not a best solution. So we can do linear regression, we have a line to fit the data, right? Fit the data, seems okay. Then we define 0.5, a line here, then we reached here. So then we, from this line, we can see on the left, they're all good, on the right, they are all malicious. But this is very sensitive to outliers. So if we have one more example here, then we probably will need to move this line to this blue line, right? Then apply the same threshold. We will end up with the line here, yellow line. So on the left, we will classify them as benign. On the right, malignant. So just because of one outlier, our classification result changed dramatically. So this is not a very good model. So one model, a different model we can take is that we take a function which outputs something like this. And you can see that if there's an outlier, the function stays the same. And if you take a decision point at 0.5, the yellow line actually doesn't change much. And you will still do the right classification. So what's the function? What is this function? So this is a very important function. It's called the sigmoid function. You don't need to go to the detail, but the sigmoid function takes input and outputs value between 0 and 1. The intuition is that if your input is very big, it outputs 1. If it's very small, it outputs 0. If it's 0, it outputs half, 0.5. Okay. So now the model. So what is the model? The model is that we have multiple inputs. In this case, the first can be the size of the tumor. The second could be the color of the tumor. The third could be the shape of the tumor. Note here I extended the one input to multiple inputs. Now we have like color, shape of these things. But the solution stays the same. Then we feed them, we multiply these inputs by the weight, theta 1, theta 2, theta 3. By the way, these three thetas are the parameters we want to learn. We feed them into the sigmoid function, and it will have an output. So this is our model. And we hope by choosing the correct theta 1, theta 2, theta 3, the output will be close to the actual labeled result. Cost function and the gradient descent to do the partial derivative. We'll skip this one. But what we need to know is that with this cost function, which reflects how bad our estimation is, and by minimize this cost function, we'll be able to eventually learn the theta. Okay, so put it together. It's actually the scenario is exactly the same as linear regression. So we have a training set, a lot of tumor size and benign or malignant, and feed into training algorithm. Then we do the estimation. If it's not good, we improve it. Not good, improve it. Eventually, we learn all the thetas. So in this example, you can see only the hypothesis is different, only the model is different, scenarios. So summary, what to take away from this model? So, and what's important for neural network is that first is the sigmoid function, the shape of the sigmoid function. And the second, to notice what are the input. So we have this x0, x1, x2 as the input. This is the size, say x1 can be the size, x2 can be the shape, x3 can be the color, something like that. We take one example and these three values are the input. So third, what to learn. We want to learn theta 1, theta 2, theta 3. So why we are interested in the sigmoid function and the logistic regression? Because if we put many, many sigmoid functions together, what we'll get? We'll get a neural network. Here I will do a quick demo about the logistic regression. I will also do a linear regression, so you will see where the run is. Okay, so this is the data. The goal is eventually to learn a line from here. So after 5 seconds, it learns a line. That's a very quick demo. Then logistic regression is more than that. These are two sets of data, red and blue. The goal is to learn a line, to classify them. So yeah, to learn a line, to this one. So on the right, they should be red. On the left, should be this is logistic regression. That's a quick demo of linear regression and the logistic regression. Come back to the presentation. Okay, that concludes the logistic regression. Now we move to neural network. First, I'll give you the problem. So the problem is that we want to learn handwriting recognition. So what's the input? The input will be obvious, 504, the pictures, handwritten pictures, and we expect the output to be correct, 504. So in this example, what's the input? That's the thing we feed into our program. So the thing we feed is actually 28 by 28 pixels. And the value will be the color of that pixel. So one sample input will be like 0, 0, 0, 0, somewhere 0 0.3, 0 0.5, here 0 0.5, 0 0.7, something like that. Then a bunch of 0, then 2, 3, 0 0.8. So the value will put it between, normalize it between 0 and 1. So you will see something like that. And the output, the correct output, of course, is we expected. It will tell us by this input, it will tells us it's fine. So then we'll go through all the samples, same technique, go through all the samples again and again, learn some parameters, how it will do the right classification. So then we present the model. So there's the reason we call it a neural network is because there's some similarity between a human brain, physical neuron in human brain, and the sigmoid function. So a neural cell in the human brain will actually take input electric signals, I don't know if it's electric or not. So it will take signals from the input, dendrites, from the dendrites, and the nucleus will process it, process inputs from these dendrites, and it will output some signal to the axons. All the neurons will be connected to each other, then it kind of similar, it makes a neural network. So that's how the name comes and why we call it, how the name comes. Okay, so now I'll show you a big picture. Before I just show you one neuron. Now the big picture is that we will connect neurons, the yellow circles, all together. The axes are just inputs, as I mentioned, the 0, 0, 0.3, 0.5, something like that. So we connect all the neurons, all the inputs into three neurons. Then the neuron will have outputs. Then we connect the neurons to a final neuron, one neuron. The output will be the input of this neuron. Then there will be another sigmoid function sits here and gives output. So then the output we want the output to be close to the actual result. Okay. I think I will skip the formula. I probably will skip the formula here. So how do we do multiple outputs? So the previous model gives it as true or false, right? So if it's close to 1, it's true, close to 0 is false. How do we do multiple? It's easy. The first neuron will tell us if the independent return picture is 0 or not. The second one will tell us if it's 1 or not. Third, if it's 2 or not. So then we'll get output like this, 0.3, 0.9, 0.1. Then we pick the highest. So the network is very confident. It should be 1, 2, 3. It should be 3, right? In this case. So this is how we can change this network to do multiple classifications. Okay, a little bit about the implementation. So to implement this one, to actually run this one, there's two important techniques. One is called forward propagation. Actually, it's pretty simple. You just take all these values by applying the formula you saw before. Then you can calculate this layer, and after calculating this layer, you apply the formula and calculate this layer, then you have an output. This is forward propagation. Backwards propagation is actually the core of neural network. The reason is that, look at this picture. You probably can imagine it's very hard to do partial derivatives of all these weights to learn the gradient of them. So there's a technique to learn them one by one layer by one layer. It uses the chain rule of calculus derivative, so that allows we to mathematically go from the layer by layer. So eventually to learn the derivative, partial derivatives, then we know how to do the gradient descent. To put it together, it's the same as the previous model. We have a different hypothesis. Then we just train it again and again. What to take away is that now the neural network is a very powerful nonlinear model. It can almost simulate any function. The other thing is that the back propagation is a very clever solution. Mathematically, it's useful to solve deep learning neural networks as well. Demo. So I'll just show you the final result. We'll not show you how to train it. It takes like 10, 20 minutes. So, okay, so now we have a picture, 0. So it should output 0 here. 0, 0, picture 0. The pictures keep changing. It's 1 now. So now it tells you it's 1. Tells you it's 1. It's 1. It's 1. Then it will change it to, the picture will change it to 2. I hope yes, into 2. It tells you it's 2. So this is a quick demo. So how after training, this neural network will be able to correctly classify the images. Okay, we have 5 minutes and now we reach the final one, deep learning neural network. The model at a glance. So deep learning neural network reflects artificial neural networks composed of many layers. At a glance, you can see it have more layers, and the layer kind of have structures. Specifically, I will talk about the convolution layer and pooling layer. So there's a limit of neural network. As you can see on the right, this is a neural network. When all the neurons are connected to each other, to every neuron in the adjacent layer, such kind of network are very hard to train. Especially look at this picture, the top left and the bottom. It's necessary. Sorry, there's some background noise.
Other listeners, please mute your mic.
Okay, thank you. Page up. Oh, interrupt. Okay. So continues. So look at the top left and the bottom right. So you can see that because all the inputs are connected to the adjacent layer, the model actually treats the input pixel exactly on the same foot. But is it necessary to relate the top left pixel with the bottom right pixel? Probably they're not so closely related. That inference, we can improve this neural network. There's still some place we can improve. So to solve this problem, we introduce convolutional layer. So we don't connect every pixel together. We only connect adjacent pixels in a small localized region. We call this region as local receptive field. We take all these regions value as the input of the next layer. So how do we divide it, this small area, 5 by 5, say? How do we say this 5 by 5 and then where's the next 5 by 5? We don't know. So what we do is we take every possible 5 by 5 areas. We just shift this input a little bit to the right, just by 1 pixel. We do it again, moving it to the right. Then we go down 1 pixel, then we do it again. So by doing this, we actually covered all the areas, and we are not putting some assumption into the input layer. How should we divide them? One more thing about the convolution layer is that they share actually the same thetas, the thing we want to learn. The reason is, by sharing the thetas, it means this layer all these neurons will try to learn the same feature. So, say if we move a small part of a cat, if we move the cat a little bit to the right, you can imagine it's still an image of a cat. So that's why we want to set the same weight, same theta for all those areas. Okay, after applying the convolutional layer, we'll do a pooling layer. So what the pooling layer does is it takes the output of the hidden layers, previous layer, and there's one way to do it called the max pooling, and it only takes the maximum value of these 4 outputs. So the idea is that if in a small area you noticed a line, or a circle, and you're sure, quite sure it's a line, not a circle, then the input to the next layer will be a line. Just forget it's a circle. Right? Okay, so yeah, I'm closing up. So then there's not only one feature you want to learn. Maybe you want to learn the shape, maybe you want to learn the direction of a line. So we can usually apply multiple feature maps to this deep learning neural network. And to put it together, then we connect the original neural network at the end, the fully connected neural network at the end of the layers we have discussed, the convolutional layer and the pooling layer. Then we get an output here. So this allows our neural networks to go deeper. So to put it together and conclude, mathematically, the backpropagation still holds the same, and the cost function still holds the same because it doesn't consider the layers internal. It only takes the input and output. To give you a visual look of how deep learning neural network learn things, these are the convolutional layers. I think these are the pooling layers, and eventually there's a fully connected neural network at the end. So this concludes how we build a deep learning neural network on top of the existing neural network. Okay. So actually that's it. I'll mention a little bit of reference and where to go deeper. All the programs I have shown you actually can be accessed from GitHub. There's a link. I haven't implemented the deep learning. I plan to do it in the future. The presentation comes from the following three sources. The second one has a very nice proof of backpropagation, but he only gives half of the proof. The rest can be found in my project here. If you would like to study the math behind it, I think linear algebra and calculus are required. So thank you very much for giving me this opportunity to do this presentation and review what I have learned. Thank you.
Okay, due to time limitation, we need to stop recording and end the meeting. And now we'll start it again for the next section.